now in the Geneva University, in Switzerland, in the group of Marcus Lütticke. He did his PhD in the University of Copenhagen.
Well, actually the Technical University.
Yes, Technical University in Copenhagen, with Professor Angelica Jarko. And then he moved to Harvard, to a group of Professor Lukin, sorry. And very recently he moved to Geneva, to the group of Professor Marcus Lütticke. He has been studying many things in quantum transport, in mesoscopic physics. He has worked on nanomechanics, on graphene and quantum computation, time-dependent transport, etc. So he has already studied many different aspects on quantum systems. And today he's going to present a kind of overview of his more recent work on continuous statistics in quantum systems.
All right, so thank you, Rosa. And first of all, I'd like to say thank you for inviting me here to this wonderful island, where I can enjoy not only good science, but also the nice weather and the wonderful surroundings. So it's really a pleasure to be here. So today I'll speak about some of my work on counting statistics of electron transport in nanostructures. And this was work that I started during my PhD a few years back. And ever since then I've tried to sort of leave the field, but every time I've tried to do that, something new has been popping up. So I'll try to give you an overview of some of the things I did in the beginning, and then also some more recent work. And of course I work as a theoretical physicist, but I'm always interested in some actual experiments. So here are some examples of some actual structures. And I mean, I'm not going to talk specifically about these particular systems here, but it's just to give you an idea about what kind of systems you could have in mind. So here are two examples of nano-electromechanical systems. So we have a little nano-resonator here sitting between two electronic leads, a source and a drain electrode. And you can now apply a bias across these two electrodes and have electron transport through the tip of the resonator. You can now imagine when you have electrons flowing through the tip, you can excite mechanical vibrations. Vice versa, once you have mechanical vibrations, that can also feed back and affect your currents. So you have an interesting interplay between electrical and mechanical degrees of freedom. So these are two nice systems. I'll also be talking about different quantum dot systems that you see here on the right-hand side. So I'll start with a brief introduction to counting statistics to sort of tell you about the main quantities and the philosophy in this field here. So basically what we're interested in is some kind of transport setup where we have a flow of charges that hit some nanostructure or just a barrier, and we're then interested in the probability distribution for the number of charges that have been collected here on the right-hand side during a time span 0 to t. So a very simple example here would be if these charges are just uncorrelated classical particles and they go through this barrier with a rate gamma. In that case, we're just looking at a Poisson process, and it's easy to write down this probability distribution for the number of collected charges here on the right-hand side. It's nothing but a Poisson distribution given in terms of the rate gamma and time t. And here on the lower figure, I then plot the Poisson distribution for different times. So you have the number of transferred charges and the probability, and then for different times given in units of the inverse rate gamma. As you can see, as time goes, the peak of the distribution moves to higher values of n, but of course as time goes, more and more electrons are collected here on the right-hand side. And also we see that the distributions gain some width. So in the beginning it's a narrow distribution, but it becomes more and more broad with time, so the uncertainty in the number of charges that have been collected grow with time. So this is because, of course, it's a stochastic process. Now for comparison, I also plot Gauss distribution with the dashed line here. And I chose the Gauss distribution such that it has the same mean and variance as the Poisson distribution. And now you would say, well, okay, this actually looks like they're basically identical. So there's no difference between the Poisson distribution and the Gauss distribution. And okay, it's true to some extent, but as I'll now show you, it's not the full truth. And actually, if you look more closely at the tails of the distributions here, you will get a different picture. So the way I look closer on the tails is simply by just taking the logarithm here, or plotting it on a logarithmic axis. Now we get a quite different view here. So this is basically again the same distribution, plotted here for t equal to 75 inverse gamma. And you see here the peak of the distribution is very well captured by the Gauss approximation. So it pretty much looks Gaussian here around the peak. But as soon as you go into the tails of the distribution and look at some of these more rare events, then you see that suddenly the Gauss distribution breaks down, and you cannot account for these rare events by just making a Gaussian approximation. So that's really some dramatic differences here between the Poisson and the Gauss distribution. So how do we quantify that? Well, one way is to look at the moments, or as I'll introduce in the following, the so-called cumulants of the distribution. So let me just remind you that if you have a distribution, then the first cumulant, and here I write cumulants with double brackets and moments just with single brackets. The first cumulant is just the mean of the distribution. And the second cumulant is the variance. One can also define the third cumulant as the so-called skewness. And in general, to define, say, the mth cumulant, we need to introduce a so-called cumulant layering function. And the mth cumulant is then the mth derivative of the cumulant layering function with respect to chi, which is the so-called counting field. And so let me just define the cumulant layering function down here. So the cumulant layering function is basically a sort of Fourier transform of the probability distribution, where the Fourier variable here is chi, which is known as the counting field. You take the logarithm of this, then you get the cumulant layering function. And if you now try to use this definition and take the first three derivatives, you will easily get this result here. And now you can also then define the higher order cumulants. Now, if you just plug in this result for the Poisson distribution in this definition, calculate the various derivatives, you will see that for the Poisson process, all the cumulants are the same. They're just gamma times t. If you instead take a Gauss distribution, you'll see that it only has a first and a second non-zero cumulant. All higher order cumulants are zero. The cumulants, they can be good to somehow quantify the deviation from the Gaussian picture. Just to say here, well, general non-zero higher order cumulants reveal non-Gaussian behavior. And in counter-statistics, the philosophy is now that we want to look at transport through some nanosystem. We then want to look at the cumulants, and then from those, hopefully be able to understand what's going on inside our nanosystem. Okay, so this was a brief introduction of the main concepts in counter-statistics, and then this is the program for the rest of the talk. So I'll spend a few minutes on describing the general methods and formalism that I use, and then I'll move on to some particular examples. I will describe one of these nano-electromechanical systems and show how you can gain information about the system and the dynamics of the resonator by looking at the charge transport statistics. Then I'll discuss some more recent work where I was asking myself, what information do I actually get from high order cumulants? What can I expect from high order cumulants on a very general level? And then finally, a very recent work on a so-called isoscopic capacitor. That was a system that was made in Paris, very small capacitor where they can control the number of charges sitting on it, so they can, by changing periodically the voltage, they can absorb and re-emit single electrons at the time. And there was some nice experiments on this system, and we made some theory that we think can explain their measurements. And I list a few relevant papers here. There's a PL from a few years back where there was a general theory for calculating counting statistics. Then there's a proceedings of the National Academy of Sciences where we give some results for these high order cumulants. And then there's this rapid PRB which is coming out this week on the mesoscopic capacitor. And finally, there's a long paper out on Conrad now which has a lot of details. And in this talk, I'll try to not spend too much time on the technical details because it can get very technical. And here I just want to focus on the main results. Okay, so the sort of generic setup that we consider is looks like this. So basically we have a little nano-scale system which is coupled to left and right leads of non-interacting fermions, and we then want to apply a bias across and drive electrons through the system here. So they serve as particle reservoirs, and at the same time we can imagine that our quantum system here is coupled to some external heat bath which can provide energy dissipation and relaxation and so forth. So this is kind of the standard setup that we look at. And we can of course write down a Hamiltonian for the full system, the full many-body Hamiltonian, which consists of these various parts here. So there's a Hamiltonian just describing the nanoscale system and the various states of that. Then there is a term that describes the tunneling of electrons between the leads and the system. And the leads here, they're usually described as non-interacting free fermions kept at a particular chemical potential and temperature, and possibly coupling to a heat bath. And the bath here is then typically described, for example, as a bath of harmonic oscillators or some kind of Calvert-Leggett model here. So this is the generic setup that we look at. And now there's a very important quantity here. That's the reduced density matrix of the system itself. So we obtain this by tracing out all external degrees of freedom. So we trace out the leads and the heat bath, and rho now only describes the state of the nanoscale system here. This is now a particular sort of type of density matrices. It's a so-called n-resolved density matrix, and that means the following. So rho here keeps track of the state of the system, or how the different many-body states are occupied, but it also has this little index n. And that's now an index that keeps track of how many electrons have tunneled through the system. This is referred to as an n-resolved reduced density matrix. Some of you work in quantum optics, you might be familiar with this because it comes from quantum optics. There's a long story in quantum optics. But also recently it's been applied to describe, for example, superconductors, and now here in fluid statistics it's also become very popular. And the key point is now that once you have your rho of n of t, but then you can trace over the system degrees of freedom, and then we actually get access to our probability solution, which is what we eventually are after. And you can also do this Fourier transform where you introduce the counting fields, and then if you use the definitions that I showed you previously, you'll see that the cumulative function is simply given by this trace over a rho in the counting field space. Okay, so now as I told you, we trace out leads and environment, and then we're just interested in the dynamics of the system itself. And this is it's easy to say, but it might not be so easy to do, because of course you have to trace out these degrees of freedom in some suitable way that fits with your system and fits with your various approximations. So in general, this is a difficult task, but there are of course known methods. For example, if you work in the weak coupling machine, so you assume that the system is only weakly coupled to the leads, then you can use Fermi's golden rule, so you simply diagonalize your system Hamiltonian, and then Fermi golden rule tells you what are the transition rates between the different eigenstates. Some of these eigenstates will correspond, or some of these transitions will correspond to electrons tunneling in and out. So this way you can eventually write down what we call a master equation, or in this case a Markovian time local equation of motion for this rho of chi comma t, with some operator here that generates the time evolution. This is perhaps the simplest way of doing it, but there are more advanced methods. There's something called magnetic transit, there's real-time diagrammatic methods, and so on. Many different ways, but for now I just assume that I end up with a relatively simple Markovian equation. If this should be non-Markovian, we can also retreat it. That's a bit more tricky. So for now I just stay at this level here. So assuming that I can write down this equation, I can in principle formally solve it. I just exponentiate my chi or w of chi times t, and then some initial state here. And typically in this field we're interested in, say, the long time stationary behavior and fluctuations around the stationary regime. So we're looking typically at the long time limit. And it's very easy to show that, well, if you look at, take a large t here, well then it will be the eigenvalue of this operator with the largest real part that will dominate the evolution. And so for large t, we'll simply have an exponential growth with this particular dominating eigenvalue determining the evolution. Now if you go back and compare with the definition of the cumulative function, you actually realize that this thing that pops up here in the exponential is actually nothing but the cumulative function. So now I know how I can calculate my cumulative function and also the various cumulants. Now you might say, well, so if I have my cumulative function here, I now just get the various cumulants here by taking the various derivatives with respect to the counting field here, and also I can define cumulants of the current, which is then simply just this one here differentiated with respect to time. This was shown a few years back by Vargas and Nazarov, and I also did some related derivations during my PhD. Anyway, but now the key problem is, okay, if I now write down these equations and I now have a general in by in matrix, well, how do I then find this particular eigenvalue? Because not only do I need to know it, I really have to have it analytically because I want to do derivatives with respect to chi. And okay, if I have a 2 by 2 matrix, fine, I can calculate 2 eigenvalues and find the one I need and take the derivatives. But if it's a 10 by 10, then it's not easy, and 1000 by 1000, then it's really a problem. So this is really a practical problem, and fortunately it has a solution. One can do a perturbation expansion in the counting field. Remember, in the end I do derivatives with respect to the counting field at 0, so chi is a smaller quantity, and I can do perturbation theory in that. And then one can develop a recursive scheme for calculating these various cumulants. This is a very short story I'm giving you here, and there are some more details here. But now I just want to give you a flavor of the approach here. So if you didn't get all the details here, don't despair. I won't be needing it much in the rest of the talk, but I just wanted to give you sort of an idea about how we proceed. So let me now turn to a particular example of an nano-electromechanical system. And again here, you see these two examples here, where you have source and drain electrodes and a resonator here with a conducting chip. So from the theoretical point of view, we look at it like this. So again, I have two leads here, and then have my tip of the resonator here. I assume it's operated in the Coulomb blockade regime, where only a single electron at a time is allowed to jump onto the tip. And then at the same time, I imagine that there's some mechanical degree of freedom, so the quantum dot can move back and forth because it's sitting on this tip here. And I'm now interested in calculating the counting statistics. So I can write down a Hamiltonian for the system. So just have a single level here, which is with energy epsilon 0. And then I have a harmonic oscillator. This is my mechanical degree of freedom. And there's a coupling between the mechanical degree of freedom and the electronic part, because once there's an electron on the tip, there's an electric field that introduces a force on the resonator. So there's a say kind of electron phonon coupling here. Then there's a term which describes tunneling between the dot and the leads. And this now is position dependent, because once I move my tip closer to one of the leads, the probability of tunneling increases. So there's a position dependence in this tunneling term here. And now we have sort of an intricate interplay between mechanics and electronics. Then I have my leads, that are the free fermions here, and there's a term which describes damping of the resonator. Now the next step is that I trace out these external reservoirs. This is not completely trivial, but can be done. And I then end up with a Markovian master equation for my rho of chi. And here you have the operator W. Now consists of three parts. There's the one first here, which is called the coherent part. That's simply the evolution of the system, the dot and the resonator. It was just isolated from the rest of the world. Then it will just propagate coherently. But additionally, there is a damping term which describes damping of the mechanical vibrations. And there's a term that describes tunneling from the dot and onto the leads. And this, of course, here you would have a counting field dependence, because in this term you describe the processes that transfer electrons. So this system has been studied in quite some detail, and some people refer to it as a charge shuttle. Ideally, people would like to have some system where you basically just have mechanical vibrations, and in each period you carry one electron from the source to the drain. So they call it a charge shuttle. Okay, yeah, let me just say, to do calculations here, I'm facing the problem that I have a harmonic oscillator, so of course I will have infinitely many states. So what I do in the calculations is that I cut off and say I only include the first 100 oscillator states. But that still makes this W a 20,000 by 20,000 matrix, and that's why we need some of these conservative ways of calculating the various cumulants. So here are some results. What I show you now is the first cumulant, which is the mean current, and the second cumulant of the current, which is nothing but the zero frequency current noise. And I now show results for these two quantities as a function of the damping of the resonator. So I assume I can change the damping, so it can either be strongly damped or weakly damped. And what you see here is that you basically have three different regimes or behaviors, and I'll now take you through each of them. So the first regime, that's what we call the shuttle regime. Actually what you see here is that the current is basically the frequency of the resonator over 2 pi, or basically the frequency of the resonator. Here I set the electron charge to 1. So basically it tells you here that the current is basically the frequency of the resonator. So it really carries 1 electron at a time in a periodic and very orderly manner. Because it's so orderly, you also see that the second cumulant is very small, it's basically 0. So it's basically a noiseless transport. You can understand it a bit better by looking at the phase-space distributions of the oscillator. Of course, remember we have an excited oscillator, and the phase space describes a circle or ellipse. And this is exactly what you see here. So here I showed the phase space or Wigner function of the oscillator, and you see it describes really oscillator moving back and forth. I can also plot what I call the charge resolved phase-space distribution. These are now conditioned on either being empty or occupied. So for example here, I look at the phase-space distribution given that the oscillator is charged with an electron, and you see there's a clear correlation between having a positive momentum and being charged. So that means when you move from the source to the drain, you're charged. And then this is now the phase-space distribution given that you are unoccupied. So and you see that there's a clear correlation between being unoccupied and moving backwards. So this really clearly shows that we have this kind of shuttle transport. So now I go to the other regime here and crank up the damping. So now it's really very strongly damped. Now there's a different behavior. First of all, you see that the current is much smaller. So it's not this large curve we have here. And also there's some noise in the transport. By looking at the oscillator phase space, we can also see that basically the oscillator is just frozen. So there's a strong damping, and the electrons cannot excite motion of the resonator. So basically now we just have sort of random tunneling once in a while through the tip of the resonator, and the mechanics don't really matter too much. So you have a suppression of the current and some sort of Poissonian noise in the system. So now there's this crossover regime here, which was perhaps the most surprising one. Here clearly you see a crossover between these two behaviors, but suddenly you see that the second cumulant, the noise really blows up dramatically, and this ratio of the current, so the noise to the current, which is also called the Fano factor, suddenly blows up and is on the order of 60. Now this one can understand a bit better by looking again at these phase-space distributions. I will now refer to these as the coexistence regime, and this is probably obvious why. Because you can see here on these phase-space distributions that we have a combination of the two charge transport channels. So on one hand we have this transport via the excited resonator, or we have this other charge transport channel where the resonator is simply frozen and doesn't move. So how can this explain this enhanced noise? Well, actually, one could start to wonder, well, is this the noise enhancement due to some kind of mechanical bistability where we switch between the two different charge transport channels? So we could imagine that as a function of time, that for some time we have a large current corresponding to the shuttling channel, then suddenly we switch over and the resonator is all frozen, and then we switch back again, and transport now proceeds by these switching events. This is of course nothing but the random telegraph noise. If you have random telegraph noise, you can actually relate the third cumulant to the two first cumulants and then the current of the two channels. So what we did now was then to calculate the third cumulant, and then we could compare with what we get if we take these results and plug them in to this expression here. And the good agreement here now really tells us, well, this is what's going on here. We have random telegraph noise due to switching between these two current channels. So I hope this is sort of one way I can convince you that one can obtain information by looking at these cumulants. Of course,
so the curves up there, that's the numerical simulations or experiments?
No, this is illustrations. They just illustrate, this is kind of how I think what's going on in the system. And then if I want to check it, I look at the cumulants here.
And you have to take these two values of the current from somewhere, right?
Yes, but those of course I know, because in my one channel I have this value, and in the other channel I have the other value. Yeah, so basically I have all things that enter in this equation here.
They understand that for this formula, no, it's essential to have a Markovian telegraph noise, so each jump is dependent on each one.
Yeah.
And at least in the case in which the resonator is moving periodically, I believe the jumps are independent. They should be periodic jumps. So I don't know if this formula can be.
Well, so I mean, so when I say jump, I mean switches between the two behaviors. So I think in a long time you have.
I think the statistics of the electron transfer should be different if the motion is periodic or random.
Yes, okay. I think we're seeing different things here. So there's certainly different time scales here. So we have like one time scale over which, I mean, so basically it's a slow switching. So the switching between the two channels is much slower than transport. I mean, so for example, the frequency of the switching is much longer than the resonator frequency.
So you mean that the state in which the intensity is slow is one in which the resonator is stopped? Is that what you mean? And the one in...
Yeah.
Okay.
Yeah.
And the one which is high is the resonator is oscillating.
Yes.
But then, do you have any clue where this last bit comes from? So you have either oscillating or stationary.
Yeah, I think. I mean, it's a good question. I'm actually trying to understand it a bit better. And I think, I mean, of course, I started a harmonic oscillator, but I think there's some non-linearities in this. Then you start to have this kind of buffering oscillator mechanism where you have suddenly meta-stable states. So I think you can probably think about this as some sort of nonlinear oscillator, and the noise drives transitions into that. But that's the level I can.
So you have no clue of the nonlinearity, so
no.
The elasticity of this tip or something like that.
No, actually, and not really. I don't know exactly where it is. I think it's somewhere, but I don't know exactly yet. I hope to understand it a bit better. Okay. So let me just spend one last slide on this topic here, also discussing the finite frequency noise, because what I spoke about so far was just the zero frequency noise, but of course one can also do some of these things at finite frequency. So this is finite frequency current correlators. And so here I show as a function of the damping again, and the function of the frequency, divided by the natural frequency, the finite frequency noise. And okay, there are a couple of distinct features here. First of all, there's this gigantic peak here at the second, or twice the actual frequency. And I must say, I also never really understood where that comes from, so I cannot answer that question. What I was actually more interested in was to look at the resonance here at the first, one time the natural oscillator frequency. What's actually interesting here is that the resonance doesn't appear exactly at the natural frequency, but it's actually slightly above, so 3% above the resonating frequency. And this somehow could indicate that there's also, due to these nonlinearities, there's also some renormalization of the oscillator frequency. And actually, if we go back and look more carefully at the value of the mean current in the shocking regime, we find that it's actually not exactly omega naught over 2 pi, which would be 0.159, but it's rather a few percentage larger. That actually corresponds very well to this renormalization of the resonator frequency. So we think there's also some renormalization due to this possible nonlinearities. Okay, so let me move on to higher order cumulants, because now I hope that I convince you that there's some information in the first few cumulants, and of course it's relevant to ask what can we then expect for higher order cumulants in general. And what one has to keep in mind to understand that is that cumulants are derivatives of the cumulant generating function. As already shown, you will define the nth cumulant as the nth derivative of the cumulant generating function. And there was actually some nice recent work by Barry, where he just looked at took a function, and then he was just wondering how does the nth derivative of this function, how does that look? And what he used was that the higher order derivatives of the function are determined by singularities in the complex plane. So I read this paper and realized that I could use some of his ideas to understand cumulants in general. So following his approach, I'll now consider a general cumulant generating function called S of Z, lambda. I mean, I need to do some changing the notation because you remember that I had like an I chi, and this I just turned out to be a little bit annoying in the following analysis. So I rename I chi by Z, so Z is now my counting field. And then lambda here now denotes all the parameters that I have in my system, also time. And what I assume in the following is that this cumulant generating function has some singularities in the complex plane. This of course doesn't always hold, because for the Gauss distribution, it's just a second order polynomial, so it's analytic. And also for the Poisson distribution, that's just an exponential function, so it's also analytic. But I think actually, except for these two examples, I've not yet seen a cumulant generating function which didn't have some sort of singularity. So I think it's quite reasonable to assume that we have some singularities in the complex plane. This can be bold, it can be square root, minus points, logarithmic singularities, etc. Now the trick is that we look at the cumulant generating function close to each of these singularities. And I write in a little neighborhood around the singularity, I write the cumulant generating function on this form here, where aj is just some constant depending on your function at hand. And then the mu j here is a constant which tells you about what's the nature of your singularity. If it's a pole, then mu j just gives you the order of the pole. If you have a branch pointing to a square root, then mu j is minus 1/2, and one can also do it with logarithmic singularities. So this is just my approximation of my function close to each of these singularities. Then of course I can now do the nth derivative. So it just looks like this, it's simple. And there will be this function here, which is kind of a factorially growing term that comes from taking the derivative every time I put down an a plus 1 and so on, and that generates this term here. Now, okay, so now I know my derivative close to each of the singularities, but that sort of at first doesn't seem to help me very much because I want the derivative at z equal to 0. But then actually there's some mathematics that comes to help, and there's something called the Dabo theorem. And that actually tells you that this approximation around the neighborhood actually becomes better sort of in a larger and larger neighborhood as I go to higher and higher orders. So if it's good in a little neighborhood here and here, then when I go to say the 5th order, well, now this neighborhood grows up, and you can sort of in principle just continue it. Okay, here I'm doing some kind of cartoon mathematics, but of course this can be done more vigorously. But the main point here is just that if I go to large enough orders, I can actually get my derivative here at z equal to 0 by simply summing over all these contributions evaluated at z equal to 0. So this very simple form here. And this is actually a very general result for the higher order cumulants. And by looking at that, I can now understand different things. So first of all, okay, I just introduced this polar coordinates, so I write it as the absolute value of z and then some angle here to the real axis. Plug it in my expression here, and I'll get this simple result for the higher order cumulants. And now by looking at this, I get various information. First of all, I can actually expect that cumulants grow in magnitude with the order due to this Bn here, which was kind of factorial in m. So if I go to higher order cumulants, they will actually get larger and larger and larger. Also, I see that each singularity contributes with the contribution here goes as 1 over the distance to the power of the order. That means it actually will be the closest one to 0 that will contribute mostly. And if I go to large enough order, I can simply just only look at the closest one to 0. And finally, this is perhaps the most surprising thing, is that I see now due to this factor E minus I phi j, where phi j is this angle here, I can see that if I change any system parameter, of course my singularities, their position will depend on the system parameters. So if I now change the system parameters, I can expect that my singularities move around. When they move around, the angle with the real axis changes, and then this guy here will cause oscillations of the higher order cumulants. Okay, so let me just give you a very simple example of this behavior here. Now I just return to this example that I showed you in the beginning, but now I just restrict myself to just having one particle. So I just have like one shot. So I throw a charge onto the barrier, and it can go through with probability t, or it won't go through, it's reflected with probability 1 minus t. In this case, it's very easy to write down the cumulative function. It's kind of this binomial type. And I can of course see that now I have logarithmic singularities when the argument here is 0. So I just have singularities at these positions here. That's what I show here. Okay, and then I just have to take my large N result here, and I just have to plug in the two closest singularities. They come in a complex. They're complex conjugate to each other. So these exponentials, they combine and become a cosine. And okay, these AJ here are also simple. So actually, it boils down to this very simple expression for the higher order cumulants in this example. They grow factorially with m. Then there's this 1 over the distance to the power of m, and then cosine the order times the angle here. So this I can compare now with the exact results. So now I see the yellow curves here is what I get really by taking this function here and taking the derivatives. So here I show the second cumulant. This is a function of this transmission probability t. The third cumulant, the 10th cumulant, and the 15th cumulant. And together with it, I take this expression here. And basically what happens now is that you will see the position of these singularities is given by log 1 over t minus 1. So when I change t from 0 to 1, they move along here, or parallel to the real axis, and you change this angle. And that's why now what causes these oscillations for the various cumulants. You can see the second cumulant here, the approximation is not so good. But already at the level of the third cumulant, it actually starts to agree quite well. And you can see the 10th and the 15th cumulant is nearly perfect. This behavior that if you look at high order cumulants, they will grow factorially, and they will oscillate as basically any parameter in the system. And this has actually been measured in experiments, and this is now an experiment from the group of Haug in Hanover. So they have a little quantum dot here, which is coupled to source and drain electrodes. It's operated in the Coulomb blockade regime, so only a single electron at a time is allowed to jump from the source onto the dot and then out via the drain electrode. So they apply a bias here, and then they have a stream of electrons going through the dot here. At the same time, they have this little narrow constriction close to the quantum dot, which is so-called quantum point contact, so a narrow waveguide kind of transmission channel here, and they run a current through that as well. Now the conductance of this quantum point contact is very sensitive to localized electrons on the dot. So an electron jumps in on the dot here, it suppresses the conductance here, and that suppression is then lifted when the electron jumps out again. So if you monitor the current through the QPC, you see that it switches back and forth here, and each switching event corresponds to an electron that jumps in or out of the quantum dot. So they can really in this way count in real time the number of electrons that go through here. And the original experiments for the data we used here, they counted a couple of million electrons, but now they can do it with billions of electrons. So it's really possible to get very high quality statistics. Now what we did now was to analyze how the cumulants develop as a function of time. So here I show you results for the nth cumulant, so the first cumulant, 5th, 6th, 7th cumulant, and 8th to 11th, and 12th to 15th here. And you see, as predicted, that first of all we have a growth in the magnitude, so here it's on the order of 1, it's 40, and here's now 10,000. So this is factorial growth. And also you see that they clearly oscillate as function of time. Now in the beginning I told you that for long times they become linear in time. And this is what you can see here for the first few cumulants, that they actually start to become linear. So this is really a transient phenomenon before you reach this long time limits. Then you clearly have these oscillations. This one can understand again by writing an appropriate model now for this system. We can then analyze where all the singularities, and again use this asymptotic expression here. And it turns out for these times here, we just have two singularities that are closest to zero, and with time they move from here towards to the left here towards this point here. And it's really the motion of these two singularities that then generate fluctuations here. So this is what is obtained from this expression here, and you can see the experiment here. So it's really what you see here, this experiment here. All right, okay, and now there's been some other studies where people have looked at high order cumulants, for example, in a Josephson junction. There they've seen similar oscillations, and also in a study of a triple dot interferometer. Of course, one can now ask what's actually the physics behind this, and I'm trying to understand it a bit better. And I think actually the motion of these singularities may be related to interactions in the system. So I think one can compare some non-interactive theories with interactive theories, and I think there the behavior of these higher order cumulants may actually become important. But I can't even say much more on it now. I'm still trying to understand the details. Okay, so that brings me to the last topic, the mesoscopic capacitor. And this was work done in Geneva, and it concerns this experiment. How am I keeping on time? Started at
Maybe 20 minutes?
Yeah, okay, so I'll perhaps skip a few things here, but I'll just give you the overview here. This is so-called quantum capacitor that was implemented experimentally in Paris. So basically you have a two-dimensional electron gas here coupled to a little cavity. You apply strong magnetic fields so that you have edge states around the edges of the sample here. And now when an electron comes in along an edge state, it can either continue its way here, or it can tunnel through this quantum point contact which connects the reservoir here with the quantum capacitor. So it can jump in and then take a round inside this cavity here. Now what they did in the experiment was that they applied a bias or voltage here to the cavity, and then they could periodically shift the position of the levels above and below the Fermi of the reservoir. So for example, they would start with having a low bias, so that the highest occupied state is below the Fermi level, and they would then push up the level so that the electron can escape, and then afterwards pull it down again so they could somehow suck in an electron from the ingoing edge state. Of course, once you absorb an electron from this edge state here, you sort of create a hole that continues here. So kind of once you absorb an electron corresponds to emitting a hole. So in this picture here, you would sort of have an alternating stream of electrons and holes. So in principle, if you just DC currents, the system has zero DC current because after a long time you have the same number of electrons and holes. But of course, it has AC current, and also it has AC fluctuations. Okay, in the system they could control the transmission probability T of the quantum point contact here, and there's a few other important timescales here. So there's an escape time, tau, which is has this formula. So T was the transmission probability of the QVC, and tau naught is the time that it takes the electron to go one round in the capacitor. This is the fastest time scale in our problem. So now then this escape time is defined like this, and escape time basically tells you what's the typical time scale over which you leave or you enter the capacitor. So this is quite an advanced setup, and recently they then actually managed to measure the finite-frequency, the high-frequency noise in this system. That was really quite an achievement. I think they spent 2 or 3 years on doing it, so that's a really nice paper out on this now. But we try to understand this a bit better. I'll show you the results in a moment. So basically, okay, one can write down a relatively simple sort of master equation in discrete time, which basically just tells you, so k is now my time step, and my time step length is this tau naught. So I sort of look at the evolution every time an electron has gone one round in the capacitor. You can now ask, so what's the probability of being occupied in time step k plus 1 given your state of the system at time step k. And so there are now the two regimes here. I think actually I don't have to watch out because they're different here in their paper and in our paper, because our one is when an electron is absorbed, because after one step you can either you are occupied because you're already occupied this term, or if you're not occupied, you get occupied with probability p. And so this is in the regime where we can absorb an electron, and the other regime here is the emission regime, and there you can say, well, what's the probability of being occupied? Well, that's the probability of being occupied and not emitting. So this is a very simple model, and surprisingly it actually explains the experiment quite well. So we've done both some numerical simulations of this system and also some analytic results here. And I'll just show you here some of our numerics compared with the analytics. And you see this function of time. We start with some random initial condition, but after some time it gets locked in with the frequency of the driving. We can also, so this is the quantity that they measured in the experiment. They looked at the current correlation function, averaged over time, and then they took the Fourier transform. And after a long analytic calculation, we were able to squeeze out the analytic results from this model. And as you can see now, if we compare what they measured, the dots, it fits nicely with our experiment. So this is now the finite-frequency noise measured at the frequency equal to the frequency of the period of the driving. So this is really the gigahertz regime. Okay, let me just quickly mention two limits here. We have one limit. This is where this tau, this is the escape time, is much shorter than the period. And that's when you're in that regime, then you know that basically you're sure that in each period you will emit and absorb an electron. And the only finite frequency noise is due to the randomness in when do you emit and absorb in one period. We call this the phase noise limit, and that's what they have here. And the other regime, which is when the escape time is much longer than the period, then you have many periods, and once in a while you might emit or absorb. And this is more sort of a Poisson kind of shock noise you didn't get, and you have sort of a wide spectrum, and that's also what they find here. Okay, I will skip the last few parts about the counting statistics here. Someone's interested, I'll be happy to tell you more about it, but I think I'll go to my summary here. So I've given you an introduction to counting statistics and discussed the general theory and framework that we work in. Then I talked about this nano-electromechanical system and discussed the behavior of high-order cumulants, and then finally I spent a few minutes on discussing this recent work on the mesoscopic capacitor. What I should mention here, for me personally, the interesting part of the mesoscopic capacitor was that these other systems did not have any explicit time driving or time dependency. It was all time-independent problems. But in this mesoscopic capacitor, you actually have some AC driving, and that somehow makes things a bit more complicated. All right, and some relevant literature here, and then thank you for your attention.
Yeah, this is the last problem, nanostructure capacitor. So here you need to take into account also other eigenvalues apart from this dominating
actually, yes and no. So that now I didn't show you the counting statistics part, but if you do counting statistics after a long number or large number of periods, then actually it becomes equivalent to some kind of long time limit. And there will also be one eigenvalue that dominates it. So if you look at the statistics after many periods, then it becomes kind of equivalent, and there will still be a dominating eigenvalue that determines it. On the other hand, if you would ask questions about what's my statistics after 2 periods, then you would have to have several eigenvalues.
Part of the high order cumulants, I think that what you find is independent of any physical model, any quantum or classical.
Yes.
You are
right.
properties of generating functions.
Yes.
You apply to any generating function independently of the kind of physical model.
Right. So actually, I think so. Then of course, then the question is, where's the physics then? Because if it's so general, so that's. What I know is directly now papers where people they can tell if you have a non-interacting theory, well, where will the singularities be? And then of course you can start to think about some physics, because then you know that if you now see singularities that are not where they have to be if it's non-interacting, well then you somehow know that okay, this statistics could not come from a non-interacting source. There must be interactions in the system. So that's where I hope that there can be some physics attached to it.
In the case you presented, I mean, this single barrier, then let's say the arrangement and configuration of these singularities it was very regular, right? So they all lie along a vertical line.
Yes, and there's so this one you think about.
Yeah, that's very. I mean, this is very particular.
Yeah, no, but that's actually there's a very simple reason for that, and that's simply because when you have to solve when this is zero, now we have an exponential here, and that's of course 2 pi I periodic, and that's actually so this is the periodicity due to the exponential.
Yeah, I mean, what I mean when you sum all these exponentials, in the general case when you have many singularities, I guess that they should be non-oscillatory.
Well,
you sum respect of all of them. I mean, if they're random, then they should add to zero, right?
Yeah. Okay. I see your point. Yeah. Okay. So now it becomes a bit more tricky, but let me try to explain this. So this actually I skipped this part a bit because of course you can now. First I told you that when they move, then you see oscillations, and that, this is what you see as function of time. But of course, at some point we know that it becomes linear in time. So what happens to the oscillations? Well, actually, what happens in this case here, and this took me quite a while to figure out, is that you have all these singularities that come moving in here with time. But actually, they become denser and denser and denser. And they have some kind of percolation point here. So they all move in here to this point here, become denser and denser and denser. And at some point, it actually changes from, you have like a continuum of poles, and that suddenly makes up a branch point, or branch cut. So suddenly, so there's motion, as function of time they move, but then suddenly, for long enough times, it's simply they go here, and then suddenly what you have here is a branch cut, and now the only thing that will determine your high order cumulants is the position of this branch point here, and that doesn't no longer depend on time. So that's why suddenly it doesn't oscillate function of time any longer. So that's really a tricky thing when you take this, say, long time limit and you start with many poles. They can really, actually, okay, I can explain you more about this, but it's actually, not so simple.
Well, I have a short question with respect to your model. You can apply this method also for multi-terminal system where you have different counting fields and things.
I think so. Yeah, this should work as well. Yeah. So then you just have derivatives with respect to
with respect, and then you can calculate cross correlation between the currents in different terminals.
Yes, absolutely.